In this lesson, I'll be looking at congruent and similar solids. So the first thing I look at is just kind of the simple definition of what similar solids are. And my simple definition is a similar definition to similar polygons in that they're the same shape, but they're going to be different sizes. But now, to get into the math definition, which is probably the good idea to do here, those similar solids have to have corresponding faces that are similar. So again, that goes back to our similar polygons there. And the corresponding angles are congruent as well. Now notice that the angles are congruent, the faces are similar. If you have that, then we can say that the solids are similar, our three-dimensional figures are similar. Now what I have here is I have a pair of square pyramids. And what we're going to do, or I'm going to do in this, is I'm going to go through and I'm going to look at ratios dealing with the corresponding sides, ratios of the surface areas, and ratios of the volumes. So the first thing I'd like to look at is just what's the ratio of the corresponding sides. So if I go through and I look at this, it doesn't matter which ones I pick. As long as I pick corresponding pieces, I can write a ratio. And being I didn't specify small to large or large to big, it doesn't matter which order I go in. But what I am going to do is I'm going to do the small to the large. So I'm going to take the length of the squares on the bases. It would be 12 to 18, which if I were to simplify that, that's going to simplify to 2/3, because they're both divisible by 6. Now, I could have used the heights in these two pyramids because I know those heights, and I could look at 8 over 12. Now, if I simplify that fraction, I also end up with 2/3. So when you look at the ratio of corresponding sides in this set of similar polygons, that ratio is 2 to 3. Or if you went the other way, it would be 3 to 2. I'm going to look at small to big in mine because it didn't specify. That's just the way I'm going to do it. Now, the next thing that I'm going to do is I'm going to look at the surface areas. So what I want you to do is I want you to take a little bit of time here. I want you to go through. I want you to find the surface area of, call it the little pyramid on the left, and then I want you to find the surface area of the big pyramid on the right. So push pause right now, find those two surface areas, and when you're finished, push play again. Now here's the surface area of the little one. I've already done all the work. And what I had to do in this one is to find that surface area, I had to find the length of the slant height, which would be 10 based off of the Pythagorean theorem that I did here. Now that I had that, I could go through. I found the area of the square on the bottom first, and then I found the area of all four triangles, added it all together, so I had a surface area of 384 for that small pyramid. Which brings me back here. I'm going to put that down as 384. Now if we look at the big pyramid, I did all the work again. Hopefully you have that done. Had to go through, do the Pythagorean theorem again to find the slant height of each of the pyramid, which is the height of each triangle. Now that you have that, have all the information you need. Here's the area of the square on that's the base. Here's the area of each triangle. Add it all together, ended up with 864 square units for the surface area of the larger pyramid. Put that down. Now, I want to write a ratio of the corresponding surface areas. Well, just ratio of the surface areas, and I'm going to keep it in the same order that I did on the side lengths of small to big. So I'm going to do 384 over 864. And then I want to simplify that. So if I were to simplify this ratio, you're going to find out that it comes out to be 4/9. So I have the ratio of the corresponding sides, I have the ratio of the surface areas, small to big in both cases, and the next thing I want to do is I want to look at the volumes. So again, I want you to go back now, and I want you to find the volume of the smaller pyramid, and I also want you to find the volume of the larger pyramid. Push pause right now, find those volumes, and then push play when you're done. Again, I've already done that. So the volume of my smaller pyramid did 1/3 area of the base, 12 times 12, and then times the height of the pyramid, and I found out that the volume of this one is 384 cubic units. I'll bring that down here. I'm going to put that in for my volume of my smaller one. Now if you Hopefully you did the large one as well. Volume of the larger one, doing the same thing, 1/3 area of the base times height, we end up with 1,296 cubic units. So come down here, back to my work page here. I have 1,296 cubic units. And the last thing that I want to do on this page is I want to write the ratio of the volumes, small to big again, because that's what I did on everything else. So 384 to 1,296. And when you simplify that fraction, you find out that it comes out to be 8 over 27. Now, when everything's said and done, I'm going to look at the ratio of the lengths in the pyramids, whether that be side lengths, maybe it's the length of a height, maybe it's the length of a slant height, anything like that. Go back to that, and my ratio was 2 to 3. If you look at the surface area ratio, that one came out to be 4 to 9, or 4/9. And last but not least, we had the volume ratio, which came out to be 8 to 27. Now my hope is that you're seeing a little pattern form here. 2/3 for the length. I'm going to put a 2/3 here, and I'm going to put a 2/3 here. Because what happened here is, really, we can take that 2/3 length ratio, and if we square it, we end up at 4/9. If we take the 2/3 length ratio and we cube it, we end up with the volume ratio. So what happens is, a lot of times, you see these ratios written like this. A over B would be your length ratio, and if A over B is your length ratio, then A over B squared, or sometimes looked at as A squared over B squared, is your surface area ratio. And then your volume ratio is your A over B, all of it cubed, or A cubed over B cubed. So these are the three ratios that you really want to keep in your head. Side length ratio, or any length ratio, I should say, in your similar polygons, or excuse me, polyhedron, or solids. That would be your surface area ratio for your solids, and that would be your volume ratio of your similar solids. So I'm going to look at, oops, let's not do that one. Let's come here and let's go to our next slide. So here's kind of just a little example of, if we knew the scale factor, what would we do to calculate the surface area ratio for those two similar solids? Well, we'd take that scale factor of 3/5 and we would square it, which would leave us with 9/25. Take that scale factor ratio again, and now this time if we want the volume, we'd have to cube it. So then we'd end up with 27 over 125. Very quickly we can get this, and we don't have to know any other information about the two figures other than that scale factor or the length ratio. You may want to put this on there. That would be the length ratio, also known as the scale factor. Now, if I have the surface area ratio in the 16 over 49, what am I going to do to get back to my scale factor or my length ratio? Well, I like to think of it, working backwards. If I squared the scale factor to get to the surface area, well, to get back, then I'm going to have to take the square root, and when I do that, I'm going to end up with, oops, not 4/9, sorry. If I take the square root of 16, it's 4, but if I take the square root of 49, it's 7. So 4/7. And now that I have that scale factor, I can use that to help me find the volume ratio, and for some reason I like the number 9 today. So I'm going to take that and I'm going to cube it. And I end up with 64 over 343. And then the last one I have is I have the volume ratio, and I want to find the scale factor and the surface area ratio. Well, this is where I'm going to come back to my scale factor first and think about what did I do to the scale factor to get to the volume. Well, I cubed it. So then to undo a cube, we have to take what's referred to as the cube root. So it looks like the square root, but there's going to be this little 3 in here called the index, and that says I want the cube root. So what you can do is you can use your calculator to do this. Now to do this, you want to go into the math function, so if we push that, and then if you look down to number 4, there's that little 3, that's indicating it's the cube root, or if you go down to number 5, there's an x there, so that one is saying you could take any root, the 4th root, the 5th root, etc. But I'm going to pick number 4 because I want the cube root, it's already taken care of for me, and then all I have to do is type in the 64 from our problem. That was the numerator. And we find out that the cube root of 64 is 4. So I bring this back, and I know that this is going to come out to be 4 in my numerator. And then I have to do the same thing for the denominator. I have to find the cube root of 216. So go back to my math, go down to number 4. I can either scroll down to it or just push number 4. Oops, went too far. Push enter on that. And now I have 216, and the cube root of 216 is 6. So if I come back here, this comes out to be 6, which I would always want to simplify to become 2/3. And then, to get my scale factor, well, all I have to do is take that 2/3 and square it. So I end up with 4/9. So keep those ratios for similar solids straight. Remember, scale factor, it's going to be any scale factor, your A over B. Then if you go to the ratio of the surface areas, it's going to be A squared over B squared, and the volume ratio is going to be A cubed over B cubed. And that's going to conclude the lesson portion on congruent or similar solids.